Hello, good afternoon. I am Saurabh and I welcome all of you to this session for the NPTEL course Applied Thermodynamics. So this is our session 12. This is the last week. In this session, we will discuss reciprocating air compressors. Okay, we will solve some problems as always. And I hope that this session will be helpful for you to clarify any doubts if you have, and it will be helpful for you uh, for solving the assignment problems. Okay, so let us start. This is question number 1. It says, in multi-stage compression, an intercooler is introduced between stages of compressors so that gas will enter the second stage at the same temperature at which it entered the first stage. So, you know what is multi-stage compression? You know what is intercooling? So, you know that when you compresses the air, then the temperature increases, right? For example, you have an adiabatic compression, then during the compression the temperature will increase, right? So after one stage of compression you need to reduce the temperature, and then again you can compress the air in another stage. Okay, so this is called multi-staging. So why we are using intercooling here? Because we want to make the whole process of compression as near to make the process near to isothermal as much as possible, right? Because in isothermal process, the work requirement is minimum. Okay. So what we do, let's say this is our PV diagram. We start the compression and this goes something like this. This can be any polytropic process. Okay. And if I draw the isothermal line, then it will be something like this. Correct? Okay, so this red one is isothermal line. This is isotherm. Isotherm means PV is equal to constant. And from A to B, this is any polytropic process. Okay, so A to B, this is first stage of compression. Then you can place an intercooler between two stages, which will cool down the air to the initial temperature of air. Okay, initial temperature means the temperature when you started the compression. Okay, so this red line, this is some constant temperature. Okay, so T is equal to constant, right? So from B to C, this is intercooling, and from C you can again start another set of another stage of compression. Okay, so C to D, this is uh, pardon for. From C to D, this is another stage of compression. Okay, and complete the cycle. You can join these lines like this. Okay, A to B, B to C, C to D, E, F, G, H. Okay, so you have compressed the gas up to pressure P2 and you started from pressure P1. If you are doing the compression is two stages and compare this thing to the case when you are doing compression in one stage, then this area, okay, if you are doing the compression in one stage, then it would have been something like this from B to D dash maybe. Okay, so this would have been compression in one stage from pressure P1 to P2. But if you are using intercooler, then this shaded area, this is the amount of work done which you have reduced because you are using an intercooler. Okay, so sorry, so this is saving in work input requirement. Okay, so this is what an intercooler do. Okay, so it reduces the amount of work input requirement. This red shaded area is that amount of work which is saved. Okay, anyways, now let us come to our question. It says in multi stage compression, an intercooler is placed between two stages of compression so that gas will enter the second stage at the same temperature at which is entered the first stage. Okay, so you are intercooling and you can intercool the gas, you can cool down the air up to any temperature. Okay, so that temperature can be less than initial temperature. Okay, or it can be more than initial temperature. But in case of a perfect intercooling and in case of an optimized in an optimized case, the gas should be cooled up to the inlet temperature of the first stage. Okay, why it is like this? And that can be shown by simple calculation. Okay, you can write down the expression for the total work done for two stages, and then you can then you can find what up to what temperature this gas should be cooled after first stage. Then you will find that it should be cooled up to the same temperature at which it entered the first stage. Okay, so maybe we can see this in another question, some other question, but for the time being I hope it is clear that you are able to answer this question. Okay, so this is a true statement for you know ideal intermediate, or you can say for ideal two stage pressure. Okay, so this is called perfect intercooling. Okay, so I hope this is clear and we can move to the next question. This is PV diagram. If it is clear, then we will move to the question number 2. It says reciprocating air compressors handle higher mass flow rates at higher pressure ratio, lower mass flow rate at lower pressure ratio, higher mass flow rates at lower pressure ratio or lower mass flow rate at higher pressure ratio. So you know that there are two main types of compressors. One are called reciprocating air compressors, another one are rotary air compressors. Okay. So reciprocating air compressors, I hope that you know that reciprocating air compressors, they offer very high pressure ratio. Okay. And rotary type of air compressors, they offers relatively lower pressure ratio. But rotary type of air compressors can handle high mass flow rate. Okay. Higher mass flow rate of air. But reciprocating air compressors on another hand, on another side, they can work for relatively low amount of airflow. Okay. Low mass flow rate. So this is the some advantage or disadvantage, you can say. So now I hope you can answer this question, that reciprocating air compressors can handle low mass flow rate and they can work for high pressure ratio. So which option is the correct option? So last option, lower mass flow rate at higher pressure ratio. This should be the correct option. Okay. Okay. So I hope it is clear and we can move to the next question. Okay. Question number 3. It says that by perfect intercooling, we will achieve the isothermal compression, which requires the least work and the efficiency will improve. So we have discussed this in question number 1, the perfect intercooling. So by perfect intercooling, we try to achieve the process close to isothermal as much as possible. Okay. Why? Because for isothermal case of isothermal compression, the work input requirement is minimum. Okay. But in the real case, the isothermal compression is not there. Okay. So we need some intercoolers. By perfect intercooling, we will achieve isothermal compression. Not exactly isothermal compression, but yes, we can intercool the air after first stage of compression to the temperature which was there before the start of first compression. Okay. You will achieve the isothermal which require the least work and efficiency will improve. Yes. So it is true. Okay. You will not exactly reach to isothermal compression, but you can say close to isothermal compression. Okay. And for isothermal case, the work requirement is minimum. So of course the efficiency will improve. Okay. I think it is clear, and we can move to the next question. Question number 4 says the effect of increase in clearance volume of a reciprocating air compressor is to increase the induced volume of the gas. I hope you know what is clearance volume, because you have studied this in air compressor as well as in IC engines, right? We need some clearance volume for the movement of some piston or valves. But clearance volume reduces the amount of swept volume, right? Because you cannot go above the TDC. Okay. So when the piston is at TDC, at when the volume is minimum, you cannot reduce the volume further. Okay. And that minimum volume is called clearance volume. So if you increase the clearance volume, what will happen? You will basically reduce the amount of swept volume. So if you are reducing the amount of swept volume, then the amount of induced air will be reduced. Okay. So the effect of increase on clearance volume of reciprocating air compressor is to increase the induced volume of gas. So this is not correct. Okay. This is false, because increase in clearance volume will reduce the amount of induced volume of the gas. Okay. Is that clear? If there is no doubt, then we can move to the next question. Okay. Before that, we have this graph which explains clearly how this amount of induced air or the efficiency, the volumetric efficiency, depend on the clearance volume. Here you can see that for any given pressure ratio, for example, let us take this example. Okay, for this red highlighted, okay, for this pressure ratio, you can see that if you increase the compression ratio, sorry, not the compression ratio, clearance volume, your volumetric efficiency, this is dropped. Okay, so this is being reduced when you increase the clearance volume. Okay. I hope this is clear, and we can move to the next question. Question number 5 says the ratio of the volume of free air delivery per stroke to the swept volume of the piston is known as. So this is very easy question. You know the definition of, you know, volumetric efficiency. The previous question we just discussed. So anyways, there are four options. First says isothermal efficiency. Second says isentropic efficiency. C, adiabatic efficiency, and D, volumetric efficiency. And you know that definition of volumetric efficiency is this. It is the ratio of volume of free air delivery per stroke to the swept volume of the piston. Okay. So this is just the definition, and it should be clear. Okay. It's clear, then We can move to the next question, question number 6. Question number 6 says, for reciprocating air compressor, as the value of pressure ratio increases, the volumetric efficiency, so whether does it decrease or increase, or it remain constant, or none of them. So you can answer this question if you observed that previous graph of volumetric efficiency carefully. Okay. Okay, we will visit that graph again so you can easily answer this question. You can see that for any given clearance volume, for example, let us take this B, let us say, okay. For this clearance volume shown by this dotted line, you can see that if you increase the pressure ratio, the volumetric efficiency is being dropped, okay. If you see from the top here, the pressure ratio is 1, then the volumetric efficiency is maximum. If you start increasing the pressure ratio, you can see this volumetric efficiency is being dropped, right? Okay. So for a given clearance volume, on increasing the pressure ratio, the volumetric efficiency will drop. Okay. So now you can answer this question number 6. That for reciprocating compressor, as the value of pressure ratio increases, the volumetric efficiency decreases. Okay. So the option B should be the correct option. Okay. I hope this is clear and we can move forward. Okay, so no doubt then we can move to question number 7. Okay, question number 7 says, in a two-stage reciprocating air compressor with a suction pressure of 4 bar and delivery pressure of 16 bar, the ideal intercooler pressure will be. So if you know what is an ideal intercooling, then you can easily answer this question. Okay, so an ideal intercooling is the case where the amount of work input is minimum. So what we can do, you can write the expression for total work input, and to find the ideal intercooler pressure, you can differentiate that expression with respect to the intercooler pressure, okay, or the intermediate pressure, and set that derivative equal to 0, okay, because you want the minimum. Okay, so for minima you can set the derivative to be 0 and the double derivative should be positive, but we don't need to do that because anyway we'll get the minimum only. And then you can solve that equation and you will find the intercooler pressure. Okay, or the ideal intermediate pressure. Okay, so what is the expression for work? This is n minus 1 or T1 Px. Okay, so Px is the intermediate pressure, okay, and P1 is the initial pressure of the first stage. N minus 1 by n minus 1. For the second stage, it will be same, n minus 1 or T1, but instead of Px, it should be P2, and instead of P1, it should be Px, n minus 1 by n minus 1. Okay, so this is the amount of work input. Okay, so for ideal ideal intercooler, you need W to be minimum, right? And to find the minima, you can differentiate W with respect to Px and set this thing equal to 0. Okay, so if you do this exercise, then you will find that Px comes out to be under root P1 P2. Okay, so this is not very complicated. This is just straightforward. You just differentiate with respect to Px and solve the equation for Px. Then in terms of P1 P2, you will find that Px comes out to be square root of P1 times P2. Okay, so for this question, this is two-stage reciprocating compression and suction pressure. Okay, so suction pressure is basically P1. So suction pressure is 4 bar. So this is P1, and the delivery pressure, that is the final pressure, or it is, so it is P2. This is 16 bar. Okay, and we have to find the intercooler pressure, or the ideal intermediate pressure. Okay, so Px, now you can find the Px, as we discussed, it is under root of P1 P2. So this is square root of 4 into 16 bar. Okay, this is square root of 64. So Px is how much? 8 bar, right? The ideal intercooler pressure will be 8 bar. Okay, so I hope now this is clear. So for an ideal intercooling process, what we need minimum amount of work input. Okay, and this is the ideal intercooler pressure. Anyways, so now I hope that this ideal intercooling is clear. Okay, so now we can move to the next question. There is no doubt. Okay, question number 8. Question number 8 says, in a two-stage reciprocating compressor with perfect intercooling. Okay, so again, this is a perfect intercooling process. The suction and delivery pressures are 1.5 bar and 54 bar. Okay, respectively. Both stages of compression follow the same polytropic process. Okay, the intermediate pressure in bar will be equal to. So again, it is the same question, just numerical values are changed. Okay, so suction pressure, that is P1, is given to be 1.5 bar. P2, that is delivery pressure, that is given to be 54 bar. So ideal intermediate process pressure will be square root of P1 into P2. We just discussed this in the previous question. So 1.5 into 54 bar. Okay, So you can calculate this value. Square root of 1.5 times 54. Sorry, 1.5 times 54. Okay, so this is coming out to be 9 bar. Okay, this is numerical type. Okay, so the correct answer is 9 bar. Okay, now I hope that you are able to answer these type of questions. Okay, so there is no doubt, then we should proceed to the next question, question number 9. Okay, question number 9 says a single stage reciprocating compressor takes 1 cubic meter of air per minute at 1.013 bar. Okay, so this is, I think, atmospheric pressure and 15 degrees Celsius, and delivers it at 7 bar. Okay, the indicated power in kilowatt is, we have to find the indicated power. Assume the law of compression as PV to the power 1.35 is equal to constant and clearance is negligible. Okay, so this is a polytropic process. Okay, PV to the power something is equal to constant. If it was an adiabatic compression, then for adiabatic compression, then it would have been PV to the power gamma is equal to constant, right? Okay, so we have to find the what we have to find, indicated power in kilowatt. Okay, we have to find the power. So what is power? Power is work per unit time, right? Work input per unit time. So basically we have to find the work input. Okay, or let us say 1 nm, 1 minute. Okay, so that work per unit time will be the indicated power. So basically we need to find the work input. Okay, so you know the expression for work input for adiabatic process, what it is? It is gamma minus 1 by gamma P1 V1 P2 V2, sorry, P2 by P1 to the power gamma minus 1 by gamma minus 1. Okay, so this is for the adiabatic, but here we have polytropic compression. So for polytropic compression also it is same, we just need to replace gamma by this n, PV to the power n is equal to constant. So this, instead of gamma we will use n. Okay, so work input will be equal to n minus 1 by n P1 V1 into P2 by P1 to the power n minus 1 by n minus 1. Okay, so this is the work done. For 1 minute, the amount of air that is being compressed, the volume of air V1, this is given to be 1 cubic meter. Okay, and the suction pressure, it given to be P1 is given to be 1.013 bar, or 1.013 into 10 to the power 5 Pascal. And the delivery pressure is given to be, P2 is given to be 7 bar, right? So 7 into 10 to the power 5 Pascal. Okay. And N is given to be 1.35, correct? So P to the power 1.35. So this is our N. So now you can put these values in the expression of work. Okay. So work, what was the expression? I will write it again. N minus 1 P1 V1 times P2 by P1 to the power N minus 1 by N minus 1. Okay. Anyways, so let us substitute the values. So N is 1.35 divided by 1.35 minus 1 into P1 is 1.013 into 10 to the power 5. I'm writing all the things in their corresponding SI units. So I will write the final unit for the work, that will be the joule. Okay. Into volume is, sorry, that is 1 cubic meter times P2 is 7 bar. Okay, we are writing the ratio, so we don't need to worry about Pascal or bar. 7 by 1, 1.013 actually. Okay, to the power N minus 1. So 1.35 divided by minus 1 divided by 1.3 and then minus 1. Okay, so this will be the work done per minute. Work per minute. Okay, so let us calculate this value. 1.35 divided by 0.35 into, okay, so this thing will be in the joules, into 1.013 into 10 to the power 5. 0.35 divided by 1.35 minus 1. Okay, we will calculate this thing one by one. First, let us calculate this value, maybe 1.35 divided by 0.35. This is 3.857. Then we can calculate, okay, sorry, 7 by 1.013. So it is 6 to the power 1 by 387 minus 1. Okay. Not 6, it is 6.9. 6.91. Okay. So 6 to the power is the power 1 divided by 3.857 minus 1. 3.857 into 1.013 into 10 to the power 5. Okay, so everything in joule into 0.591. Okay, so now you can multiply all these values. 857 into 1.013 into 0.591. Here it is coming out to be probably we have made some mistake. Okay, we'll have to do this again. Will this work? One point 35 into 1.013 into 10 to the power 5 into 1 into 1 into 1 into 1 into 7 divided by 1.013 to the power 0.35 divided by 1.35 minus 1. Sorry, this is also not working. We will use this calculator. Yes, good. to the power. Okay. So this is coming out to be 254,212. 54212. 254,212 joule per minute. Okay. So to convert this thing into second, we need to divide this thing by 60. Okay. 254,212 divided by 60. So it is coming out to be 4.23 into 10 to the power 3 joule per second. Okay. So you can write this thing as 4.23 kilojoule per second. And kilojoule per second is nothing but kilowatt. Okay. So you are getting 4.23 kilowatt. Okay. So this is the indicated power. I hope this is clear. 4.23. Okay. I hope this is clear. And we can move to the next question. Question number 10. Okay. So question number 10 says the isentropic efficiency of a compressor is defined as the ratio of isentropic compressor work to, there are four options: adiabatic compressor work, reversible adiabatic compressor work, isothermal compressor work, or actual compressor work. So again, this is just a definition based question. You can easily tell the answer. Okay. So you know that compressor work is minimum for the ideal case. Ideal case means when it is working in an reversible manner. Okay. Or you can say isentropic manner. Okay. So when compressor is working in isentropic uh, process, then the work input is minimum. Okay. But compressor does have some irreversibilities. So the compressor work, actual compressor work is more than the work in case of ideal case. Okay. So the ratio of that actual work, so the ratio of that minimum work to the actual work, that is the isentropic efficiency. Okay. So this is the definition of isentropic efficiency. Okay. Isentropic efficiency is minimum work, that is isentropic work, right? Divided by actual work. Okay. You know that work requirement is minimum in case of a completely reversible process. Okay. So this is very easy, right? So The correct option is the part D, right? Isentropic efficiency of a compressor is defined as the ratio of isentropic compressor work to the actual compressor work. The actual compressor work is always more than the isentropic compressor work. Okay. So this isentropic efficiency basically tells you how much irreversibilities are involved in the compression. Okay. So I hope this is also clear, and we can move to the next question. Question number 11. Question number 11 says, which of the following nature of pumping characteristic is or are true for a reciprocating compressor? So in some previous question we discussed about advantage and disadvantage of reciprocating compressor. So here are few more. So what we had discussed in previous question, a reciprocating compressor, they can handle high pressure ratio, but they can work only for lower mass flow rate. And since they are reciprocating, so they are intermittent in nature, right? Uh, on contrast, rotary compressor are continuous in nature, right? But since it is reciprocating, so it is intermittent. Okay. And this is positive displacement. The piston has some, positive displacement, right? So it is. And it is not any, moving machine, right? So it is not the dynamic machine. So now you can answer this question. So it is intermittent in nature. It is not the okay. So nature of pumping in reciprocating compressor is intermittent flow. It is not the continuous flow. It is positive displacement machine. Okay. So there are two correct options, option A and option B. Okay. Intermittent and positive displacement machine. I hope this was clear and there is no doubt. So we will move to the next question. Question number 12. Question number 12 says, the thermodynamic nature of compression process in an reciprocating compressor that incurs minimum power is isothermal process or adiabatic process or isentropic process or polytropic process. So we have discussed this many times that minimum work or minimum work process should be isothermal, right? But I will write the expression, okay, again for work, okay, for polytropic, P v to the power n is equal to constant, this W is equal to n by n minus 1 or T1 to the power P2 by P1. This is pressure ratio, n minus 1 by n minus 1. Okay. For adiabatic, this n is equal to gamma. And for isothermal, it is different. Okay. For isothermal, work requirement is P1 V1 ln P2 by P1. Okay, so if I make a chart here, then it will be more clear. But we can add another page. A, B1, B2, and B3. So here you can see that this area enclosed by this cycle is minimum for this line, B3 line. Okay, so for B3, this is isothermal. PV is equal to constant or T is equal to constant. B2 is any polytropic process. PV to the power n is equal to constant. And B1 is adiabatic. Okay. PV to the power gamma is equal to constant. So here you can see that the work input requirement is maximum for the adiabatic, because the cycle for this adiabatic process has this maximum area, right? This additional area, this additional green area will be there. Okay, I'm highlighting this additional area in green. So for adiabatic, this extra work you need to provide. Okay. Work requirement is maximum for adiabatic. Okay, so at work requirement for adiabatic is more than that for polytropic, and it is minimum for isothermal. Okay, I hope this is clear, right? So minimum power is required when the process is isothermal. Okay, so this is the reason we want our compression process to be close to isothermal process as much as possible. Okay, because for isothermal process, uh, the power requirement is minimum. Okay, I hope that is clear. Now, question number 13, it says that reciprocating air compressor is positive displacement compressor. So I hope you can answer this question, because we have discussed this in some previous question, in question number where question number 11. So reciprocating air compressor is positive displacement machine. So the statement is true. Okay, this is a true statement. Now we will move to the question number 14. Question number 14 says the actual power input to the compressor is smaller than the indicated power. So indicated power is calculated from the indicator diagram, right? From the PV diagram. And that is the theoretical value of the power requirement. But in the actual case, there are some losses as well, some friction is there. To overcome these losses, you need to put some extra work. Okay. So actual power input requirement to the compressor is more than the indicated power, right? So indicate the actual power is always greater than the indicated power. But here it is saying that actual power input to the compressor is smaller than the indicated power. So this statement is not correct. This is false, right? This is a false statement because actual power input is always greater than the indicated power input. Okay. Now we will move to the next question. Question number 15. Question number 15 says that a reciprocating compressor receives air at a flow rate of 5 kg per minute. Okay. Running at 320 revolutions per minute. The mass in kilogram induced per cycle is. So this is a very basic question. You can easily answer this question. Okay. Mass flow rate is 5 kg per minute and speed is 320 revolution per minute. And we have to tell what we have to tell mass per cycle, okay, or mass per revolution. So just divide by this thing uh, by RPM, okay. So 5 kg per minute divided by 320 revolution per minute, okay. So you will get 500 by 320 kilogram per revolution. So one revolution corresponds to one cycle, right? So we are getting 0.015 kilogram per revolution, okay. So which is the correct option? Correct option here is option A, 0.015. Okay. I hope this was easy to solve, and we will proceed to the next question. This question says, in a multi-stage compressor and a multi-stage compressor incorporates Z number of stages with perfect intercooling between the stages. The compressor receives air at pressure P1 and delivers the compressed air at pressure P2. For a minimum indicated power requirement, the pressure ratio for each stage is PS, and we have to tell what PS is. Okay, pressure ratio we have to tell. So we have discussed this in many previous questions. We have solved some questions, right? That to find the minimum power requirement, you can write down the expression for power, indicated power, or the work input. Then you can minimize uh, that work input with respect to your intermediate pressure. Okay. So anyway, we can do this for multi-stage, but for this question, let us do this for two stages. Okay. We will do this for two stage. compression, and the same will be valid for, you know, more than two stages as well. Okay, so we will start by writing the expression for work input. Okay, what is this? This is n by 1. Okay, and this I am writing for PV to the power n is equal to constant, this polytropic process, n minus 1 RT1 into P2 by Px by P1 to the power n minus 1 by n minus 1 plus the same thing, n minus 1 RT1. Instead of Px, it will be P2 now. Okay, I will write in the next line, plus n by n minus 1 RT1 P2 by Px to the power n minus 1 by n. This. Okay, and Px is the intermediate pressure. So you can rearrange this by taking this the whole thing common. So we'll get Wc equal to n minus 1 RT1 is Px by P1 n minus 1 by n plus P2 by x n minus 1 n by n minus 2. Okay, need some more cases. Now for minimum work requirement, for minimum power requirement, we can just differentiate this expression with respect to Px and set that derivative equal to 0. So now let us differentiate that. So what will we get? We will get n minus 1 RT1, in bracket it will be n minus 1, then Px by P1 to the power n minus 1 by n into 1 by P1 into to the power n minus 1 by n minus 1 plus P2 to the power n minus 1 by n into Px to the power minus 1 plus 1 by n minus 1 and minus n minus 1 by n equal to 0. Okay, so now you can simplify this. You can remove this part and some other part. It will simplify to, please, there are a few more steps. Okay, those steps you can check by yourself. I'm skipping some steps and I'm writing little simplified expression. Px to the power 1 by n plus 2 minus 1 by n is equal to P2 P1 to the power n minus 1 by n. Okay, so please complete those steps and check that you are getting the same expression. Okay, so from this you can get Px to the power 2 n minus 1 by n is equal to P1 P2 to the power n minus 1 by n. Okay, so you can, so from here you can write Px square is equal to P1 P2. So Px is under root P1, P2. Okay, so this final result we have used many times in some previous questions, right? To find the ideal intermediate pressure. Okay, and what we are asked to find this in question? The pressure ratio for each stage. Okay, pressure ratio. What is pressure ratio for first stage? Sorry, pressure ratio in first stage is Px by P1. In second stage, it is P2 by Px. Okay, and we have Px is equal to under root P1 P2. So you can divide both sides by P1. So you'll get Px by P1 is equal to P2 by P1 square root of this thing. Okay, or you can write P2 by P1 to the power 1 by 2. Similarly, if you divide this thing by P2, you will get Px by P2 is equal to root P1 by P2. Or you can write it as P2 by Px is equal to P2 by P1 to the power 1 by 2. Again, the same thing. Okay. So compression ratio for each stage is coming out to be P2 by P1 to the power 1 by 2. And since we are doing this calculation for two stages, we are getting 1 by 2. If there are more than one stage, more than two stages, let us say Z stages, then you will get 1 by Z. Okay. You can try this calculation for, more than one stages, more than two stages. Okay. So the correct option is this, right? P2 by P1 to the power 1 by 2 or 1 by Z for Z stages. So correct option should be part B. Okay. I hope this is clear. This was the last question. So now you know the basics of, reciprocating compressors. And there was one question in refrigeration where there were some concepts related to air compressors. So now I hope you can solve that question by yourself. Okay, because now you know all the definitions. Okay, so in this session we have discussed uh, the work requirement for for isothermal cases minimum. So we want to keep our process close to isothermal as much as possible. So to do that, we do multi-staging, and we discussed that reciprocating air compressors can handle, very high pressure ratios, but they work with uh, relatively lower mass flow rate. They are positive displacement machines. Okay. We discussed the effect of clearance volume on the volumetric efficiency, and we also see that on increasing the pressure ratio, the volumetric efficiency drops, right? We discussed that then that ideal intermediate pressure is the square root of the multiplication of final pressure and the initial pressure. Okay, we discussed that the actual compressor work is always more than the theoretical work. Okay, and we discussed that reciprocating machines are intermittent in nature, right? We discussed that to find the ideal intermediate pressure, we can differentiate the expression for work input with respect to the intermediate pressure and set that derivative equal to 0. And we also discussed by graph that adiabatic compression has maximum work input requirement and isothermal has minimum work requirement, and polytropic is in between isothermal and adiabatic, right? So I hope that everything was clear, and I hope that this session will be helpful for you to solve the assignment problems. Okay, so we will stop here and we will meet in the final session that will be our review of all these lectures. Okay, the final session. Till then, take care. Thank you.